Hey, Dr. Clark coming back at you with another video here. This time we're looking at force of interest. Let's dive right in. So, what is force of interest? Well, force of interest is getting at nominal interest rates. Okay, so think nominal interest rates. We're going to specify the number of compounding periods per year. Okay, and we've seen this with, for example, APR. APR is compounded 12 times per year, and a bank loan often gives you the APR, the nominal rate with monthly compounding. Bonds pay the coupon semi-annually, so they're using nominal rates with semi-annual compounding. So nominal rates we've played with, but now we want to think about the concept of more frequent compounding. So what happens if we compound it more than 12 times a year, something like that? Okay? Now, if you're wondering, well, why would this be important? Well, imagine a highly fluid account with money moving in and out on a daily basis. They might want their compounding happening daily, but you might even imagine, what if you had $1 billion in an account for a few hours? You might want hourly compounding, because however many hours that $1 billion is in that account, maybe you want it that much. Okay? So what we're going to do is we're going to play with nominal compounding where the compounding period gets very, very small. So faster than every day, faster than every hour even. Okay? That's the game. So the motivating question is, how do you connect the effective interest rate? How does that depend on the number of compounding periods if you have the same fixed nominal rate? Is there a limit to the effect of increasing the number of compounding periods? And how do you solve time value of money problems if they involve the force of interest? Once we learn what force of interest is, then that question will make sense. All right. So here's our motivating example here. You've received an inheritance from a long-lost uncle, and you now have $100,000 to invest. Okay. You're looking for a reasonably secure investment for the next year, and then you're going to figure out your long-term strategy. So you found a bunch of one-year CDs. That gives you a year to figure out what you're going to do in the long term. Okay? And CD1 is 4% nominal with semi-annual compounding, so that would be 2 times per year. Number 2 has monthly compounding, so that's 12 times per year. Number 3 is annual compounding, so I guess that's just 1 time per year. And number 4 has daily compounding, so that's 365 times per year. So what's the effect of compounding it different numbers of times per year? Okay, so let's take a look at CD1, which had 4% interest, semi-annual compounding. 4% nominal with the old semi-annual. So what we can do there is we can say the effective annual interest rate would come from taking that 4%, dividing it in twain, and raising it to the second power. And if we do that, we get 1.02 squared. That gives us 1.0404. So basically 4.04% effective. Okay? So if you take a 4% nominal rate, the effective rate will be higher. That's CD number 1. What about CD number 2? CD number 2 was 4% nominal with monthly compounding. All right? So we're going to take that same 4%, we're going to divide it in 12 and then raise it to the 12th power. So we're going to get whatever 1/12 of 4% is, but we're going to get that interest 12 times in a year. And if we run that on the calculator, we're going to get 1.04074. So this is actually 4.074% effective. Okay, so here the I is 4.07. Here the I was 4.04. Now, you notice when we compounded it more often, we got a larger effective interest rate. All right, let's take a look at CD number 3, which had annual compounding. Well, annual compounding would just say take your 4%, and you get that 4% one time per year, so that's 1.04. So you just get 4%. Okay, well, 4% nominal compounded once a year is 4%. All right. And then the last CD had daily compounding. Daily compounding, 365 times per year. So what is the interest rate that you would get if you took your 4%, divided it by 365, and then raised it to the 365th power? Maybe you want to work that alongside me on your calculator and see. I get 1.0408. Aha! Now I'm getting, what is that? 4.08% effective. And that is, if I'm not mistaken, larger than the 4.07% effective that I got just a minute ago with a monthly. So it seems like the more frequently you compound it, the bigger the effective interest rate is. This is the general formula. If you have a nominal rate compounded m times per year, that's the formula that gets you to the effective interest rate I. Okay, so that's not new, but that's something that you want to know. And what we just saw as the more you compound it, the more times per year, the larger that effective rate will be. And that's the conversion formula. Let's keep going. This is a table. And let's say you take your $104,000 you invested at 4% compounded annually, that is 1.1 time per year. You're going to end up with $104,000 after 1 year. If you compound it semi-annually twice a year, you're going to get 0.0404 effective, which means you're going to get 104,040. You're going to get more money if you compound it more and more times. So as you increase the number of compounding, you shrink the length of the period, but you increase the value. Look at that. Every single number is getting bigger and bigger and bigger than the one before it. So the effective rate goes up as the number of compounding periods go up. Let's do that again. Semi-monthly, that's 24 times a year. Weekly is 52 times a year. Daily, 365. Hourly, 8760. Minutely, 6,000 times. And every second, you could compound it 31,536,000 times in 1 year. If you increase the compounding, you increase the net value. But look at this. It seems like there is a limit to how much it matters. When we went from hourly to minutely, we went up by 70 cents. But when we went from every minute to every second, we didn't go up by anything. Maybe there's more decimals down here. But it seems to be kind of leveling off. Okay? And in fact, I've got a graph and that shows that. As you increase the number of compounding periods per year, that balance goes up, but it seems to kind of level off as if there's some kind of barrier. You can't get infinite money by compounding it infinitely many times. It levels off right there. Okay, and that turns out to be true. There is a limit to how much money you can get by increasing the compounding more and more and more. Eventually, it doesn't matter. Basically, once a minute is about as it's almost like there's not much point going past once a minute because it's basically leveled off at that point. All right. So this is called the force of interest. Okay? So let's read this together. Suppose we have a fixed nominal interest rate R. So R is 4% in the last problem, but it could be any number. And you're going to compound it m times per year. That's the number of compounding periods. I is the resulting effective annual interest rate, and that's going to depend on the interest rate R, the nominal rate, and the number of times per year, according to this formula right here. So this is just that formula that we had a second ago. We had 4% plugged in. Well, now we've got R plugged in. And this is after 1 year. So that's the 1 year annual rate. Now what we're going to do is we're going to take m bigger and bigger and bigger, more and more times per year, once a second, like 36 million times per year. We're even going to say m goes to infinity. Now, if you've taken a calculus course, you might recognize this as the concept of a limit. If you don't, you're just going to sort of take my word for it. And so remember, this graph levels off. We call that a limit where it leveled off. Okay? So it's approaching this limit. And in a calculus class, you can show that if you increase the compounding periods higher and higher and higher, it's equal to e to the r. And e is that mathematical constant. Maybe you've seen e in high school. It's an important number. It's about 2.718. And it turns out that 1 plus I is equal to e to the r. Okay, so you can get the effective annual rate by taking the nominal rate r and doing e to that power. Okay? And so in our case, if we did, remember when r was, say, 4% nominal, if I do e to the r on my calculator, if I go e to the 0.04, that gives me 1.04081. So my effective rate is about 4.08% per year. And if I go back here, you can see I'm getting exactly 4.081 right there. So that's essentially, that's once a second. And if we do it once every nanosecond, once every billisecond, once every picosecond, you can approach the limit of what would be e to the r, and then this would ... go out and out and out and out and out. And so in that case, the I is 0408 10774 and more numbers there. Okay, so this is called the force of interest. This number r, the nominal rate, is called the force of interest. When you, we call this continuous compounding. Continuous compounding, when you're compounding it so many times per year, it's like beyond count. It's basically continuously compounding. All right? So here is the key formula. So if you have a balance, P, so some initial balance, you invest it for T years at a nominal rate of R that is compounded continuously, then this will give you the balance, P e to the RT. This is the formula you want to have written down on your formula sheet. There is a corresponding effective interest rate. Remember, we learned that I is equal to e to the r. So you can, 1 plus I is equal to e to the r. Okay, so if you want to know the annual effective rate, you can do 1 plus I equals e to the r. But if you have time t, then you get p e to the rt or p1 plus I to the t. Okay, so our definition here, force of interest. When interest is compounded continuously at a nominal rate r, we call r the force of interest. Usually the book will use this symbol delta for force of interest in place of r so that you know it's force of interest. So anytime you see that delta symbol, then you know we're talking force of interest and that continuous compounding is happening. Let's keep going. Let's do an example. So let's say an account earns interest compounded continuously. That means we're doing force of interest. If we're doing force of interest, we're using P e to the RT, or you could say PE to the delta T if you want to use the delta symbol, and they've given us delta as 0.05 in this problem. Okay, $2,000 is invested. What's the balance after 2 years? So our P is 2,000, our delta is 0.05, and our T is 2 years. So if we go to our calculator and we do 2,000 e to the 0.05 times 2, and that would sort of be in parentheses in your calculator, you will get a number, 2,000 times e to the 0.05 times 2. I'm getting $2,210.34. That is the answer to that question. That's the balance after 2 years. Is this Okay, so that's the answer to number 1. Number 2, is it better than 5% annual effective? Well, it better be better than 5% annual effective because this is, anytime you compound something, you get better, right? What would be 5% annual effective? Well, that would be 1.05 to the 2, right? You just get 2 years at 5%. If you do that, you're going to get 2205. And so, yes, it is better than, so I'm just going to say yes, this is better than this because compounding continuously is better than compounding it once per year. What is the corresponding annual effective rate? Well, we learned a second ago that 1 plus I is equal to e to the r, or in this case, e to the delta. E to the delta is e to the 0.05, so you get your Johnny calculator out, e to the 0.05. I'm getting 1.0513 if I round. So that means that the corresponding annual effective rate is 0.0513, which is, of course, better than 5%. It's 5.13%. So you can always take a force of interest and turn it into the corresponding annual effective rate just by using this formula right there. Let's keep going. An account earns 4.2% APR. What is the equivalent constant force of interest? Okay, this is a thinking problem. The first thing is 4% or 4.2% APR. That means we're actually getting an effective rate that's more than 4.2% because we're compounding that 12 times per year. What is the corresponding effective interest rate from 4.2% APR? I'm getting 1.0428. So in other words, 0428 is the annual effective. That's annual effective. Okay? And they said, find the equivalent constant force of interest. So I said 1 second ago that we have this conversion formula to go from if you knew the force of interest, you could find the annual effective. Well, if you know the annual effective, you can find the force of interest. And in this case, we know the annual effective is 4.28%, and we need to solve that for e to the delta. If you take the natural log of 1.0428, you'll get the natural log of e to the delta, and that's going to, using the rules of logarithms, give you delta times the natural log of e, but the natural log of e is just 1, sort of by definition of what a logarithm is, and the base e is the base of the logarithm. So in this case, delta, I kind of ran out of room here, but delta should just be the natural log of that number. So if you run that on your calculator, you get 0.04192. And so if you invest 4.192% interest nominal and you compound it continuously, you'll get 4.28% effective, right? And so the nominal rate is always less than the effective rate because you're compounding that, okay? So that is that problem. Maybe I can put this up here so it's sort of out of the way of problem number 2. When would a deposit of $100 double in value? Well, double 100 is 200, right? And so I've got my e to the RT or e to the delta t formula right here. I know what delta is. I just figured it out. It's 0.04192. What I don't know is how long it will take. I don't know the t that it will take to double. So what I can do is I can divide by 100, and that'll give me 2 e to the 0.04192 t. And then if I take the natural log of both sides of my equation, then using the properties of logarithms, this will just be 0.04192 times t times the natural log of e, which we just said was 1. And so this implies that t is the natural log of 2 divided by 0.04192, and that is 16.535 years. Okay. So you can answer questions like that using the PERT formula, as they often call it. All right, let's keep going. If Sophia is able to double her force of interest, will she double her interest rate? Well, that's kind of an interesting problem. So let's say you have delta 2 is twice delta 1, right? What would be the effect on the interest rate? So the interest rate from delta 2 would be e to the delta 2. And that would be e to the twice delta 1. And then if we use our rules for exponents, that is e to the delta 1 squared, and that's 1 plus I squared, right? And so 1 plus, and that's I1. So basically, the effective rate here, 1 plus that effective rate from doubling the force of interest, is equal to this. And what I'm going to do is I'm going to multiply this out here. That would be 1 plus 2I1 plus I1 squared. And if I subtract the 1, I get 2I1 plus I1 squared. So I2 is double I1 plus a little bit extra, actually. So it's actually better than double. So that's kind of cute. If you double your force of interest, you actually you double the interest rate. You double the interest rate plus more. So it's actually more than double. So I'm just going to write better than double, or maybe I could write more than double. It's more than double the interest rate. Doubling the force of interest more than doubles the interest rate. Will the doubling time on her account be cut in half? Ooh, that's interesting. Will the doubling time be cut in half? So if you want to double your account, then when we solve that problem, the doubling time, because natural log of e is 1, that's natural log of 2 divided by delta 1. Okay? So if we do the same problem for delta 2, then you would get the time here would be the natural log of 2 divided by delta 2. Okay, but we just saw that delta 2 is equal to twice delta 1 plus, no. Delta 2 is twice delta 1. Yeah, it's exactly twice delta 1, which is basically 1/2. If I call this T1 and I call this T2, then this little part of the equation here is exactly T1. Yeah, so you would, if you double the force of interest, the doubling time is in fact cut in half. You just can see it right there. But the effective annual interest rate is not doubled. All right. So there's a couple example problems that you can do using force of interest. Mostly what you want to be able to do is this formula right here. Everything is going to be based on that formula. All the problems are essentially, can you take that formula and run it on example problems? So hopefully that's making sense, and we will see you next time.